Welcome back to the deep dive. Today, we're really getting into it, tackling one of the absolute cornerstones of modern physics. It's all about light.
That's right. And specifically, this fundamental puzzle, what is light? Is it a wave like ripples spreading out?
Or is it maybe a stream of tiny particles, like little bullets? It sounds simple, but wow, the history here is quite a ride.
It really is. And our sources, they lay out this journey perfectly. It's the best way into understanding quantum theory, actually.
So what's our mission for this deep dive?
We're going to trace that scientific path, see how physicists went from this clear, either a contradiction,
Wave or particle.
exactly, to this really mind-bending synthesis that honestly changed how we see reality itself.
Okay. And by the end, you listening should have a solid handle on things like quanta, Planck's constant, the photoelectric effect.
And this core idea of wave-particle duality, it's basically the fast track to getting up to speed on this crucial bit of physics.
Great. Let's start back, way back in the 17th century. That's where the first big fight kicked off, right?
Uh-huh. You had Isaac Newton on one side. He was firmly in the particle camp, called them corpuscles.
Corpuscles. Little bodies. Makes sense.
And then you had Christian Huygens arguing just as strongly, no, light is a wave.
A classic showdown. But for a while, it looked like the wave side had won.
Yeah, for quite some time. By the early 1800s, things really shifted towards waves. The reason, well, waves do things particles don't. They interfere.
Right. They can cancel each other out or add up,
Yeah.
and they diffract, meaning they bend around corners.
Precisely. And the killer evidence, the smoking gun, was Thomas Young's double-slit experiment.
Ah, the famous one. Shine light through two tiny slits.
And instead of just two bright spots on the screen behind, you get this pattern of bright and dark bands, an interference pattern.
Exactly what you'd expect if light were waves overlapping. Water waves do that. Simple particles wouldn't.
Not at all. So yeah, the wave model looked pretty solid. Case closed, almost.
And then Maxwell came along later and put the mathematical seal on it.
He did. James Clerk Maxwell's equations were brilliant. They showed light is an electromagnetic wave, a vibration traveling through space. Classical physics felt complete. Elegant.
Predictable, clockwork universe kind of stuff.
Exactly. But there's always a but in science, isn't there?
Seems like it. So where did this elegant picture start to fray?
It hit a massive wall. A catastrophic one, really, when scientists tried to apply it to how energy works at the tiny atomic level.
Like with black body radiation. I remember reading about that.
That's the classic example. A black body is this ideal object, absorbs all light, then radiates energy based on its temperature.
Okay.
Classical wave theory predicted something completely absurd. It said that as the frequency of the light got higher towards blue and ultraviolet, the object should just pump out infinite energy.
Infinite. Whoa. Our sources call that the ultraviolet catastrophe. Great name.
It is dramatic, isn't it? Because clearly that doesn't happen. You know, your toaster doesn't suddenly vaporize you with infinite UV rays when it heats up.
Thankfully, no. So classical physics was just plain wrong there.
Fundamentally wrong. And into this mess steps Max Planck, around the turn of the 20th century.
The man who accidentally started it all.
You could say that. To make the math actually fit what they saw in experiments, Planck came up with this really radical idea, almost out of desperation maybe?
Which was?
He suggested energy isn't continuous, not like a smooth ramp. It comes in chunks. Discrete packets. You can only emit or absorb energy in these specific amounts.
He called them quanta, like little energy parcels.
Exactly, quanta. That was the moment quantum theory was born, even if Planck himself wasn't entirely comfortable with it initially.
And he gave us the key formula, E equals hf. Energy of a quantum is Planck's constant h times the frequency f.
That's the one, E equals hf. And the crucial part is that h, Planck's constant, it's this tiny, tiny number, about 6.6 times 10 to the minus 34 joule seconds.
So incredibly small. That's why we don't notice this chunkiness in everyday life, I guess.
Precisely. For you and me, energy feels smooth. But down at the atomic scale, that constant h dictates everything. It sets the fundamental graininess of energy.
And you said Planck wasn't totally sold on his own idea.
Well, he kind of saw it as a mathematical trick at first, something that worked. But he hoped someone else would figure out a deeper reason, maybe get rid of the quanta later.
Didn't quite work out that way, did it?
Not at all. Because just as waves seemed secure, the particle idea came roaring back, thanks to the photoelectric effect.
Right. This is the experiment where you shine light on metal and electrons pop off. Sounds simple enough.
Simple to describe? Yes. But an absolute nightmare for classical waves theory. It just couldn't explain the details of how it happened.
How so? What was the classical prediction?
If light's a wave, its energy is spread out. It depends on the intensity, how bright the light is. So a dim light should take time to pour enough energy onto an electron to knock it out.
Like filling a bucket slowly.
Exactly. And a brighter light should fill the bucket faster and maybe give the electron a bigger kick when it comes out. More energy, faster electron.
Okay, makes sense from a wave perspective.
Yeah.
But that's not what happens.
Not even close.
Yeah.
The experiments showed 3 things that just blew the wave model apart. Our sources really highlight these.
What were they? Let's break them down.
Okay, first, immediacy. If the light has the right quality, electrons jump out instantly. Doesn't matter how dim the light is, no waiting time needed.
Instantly. So much for filling the bucket. What's second?
Second, the threshold frequency. There's a minimum frequency, a specific color of light needed to get any electrons out at all.
Ah, so like red light might do nothing no matter how bright?
Often, yes.
Yes.
Even a super bright red light might fail, while a very faint blue or violet light works immediately.
Okay, that's weird. Intensity doesn't seem to be the key factor. What's the third failure?
Third, the kinetic energy of the ejected electrons. How fast they're moving once they're out. That speed depends only on the light's frequency, its color, not on how bright the light is.
Wait, let me get this straight. A brighter light of the right color just knocks out more electrons, but not faster electrons.
Exactly.
Yeah.
Brighter light means more electrons per second, but the maximum speed of any individual electron stays the same if the frequency is the same. Classical waves just couldn't explain that.
So, total failure for the wave picture here. Who figured it out?
Enter Albert Einstein, 1905. He looked at Planck Quanta, that ESF idea.
The one Planck thought was maybe just a math trick.
All right, Einstein said, no, this isn't a trick. This is real. Light itself travels as these discrete energy packets. He called them photons.
Photons, the particle of light.
Yes. And this photon idea just elegantly explained all 3 problems with the photoelectric effect.
How? Let's take the immediacy one first.
Easy. A photon hits an electron. If the photon has enough energy, bam, it transfers it all at once to the electron. Instant ejection. No waiting.
Like a single billiard ball hitting another.
A good analogy, yeah. Now, the threshold frequency...
Why does faint blue light work when bright red light doesn't?
Because of EF. Blue light has a higher frequency than red light, so each blue photon carries more energy than a red photon. Now, imagine there's an energy cost to escape the metal, a kind of exit fee. We call it the work function, W.
The toll gate, like you said earlier.
Exactly. A single red photon, even from a bright beam, just doesn't have enough energy, HHF, to pay the toll, W. So no electron gets out.
But a single blue photon, even from a dim beam, does have enough energy.
Correct. It pays the toll,
Yeah.
W, and the electron is ejected instantly.
And that also explains the third point, the electron's speed.
It does. If the blue photon's energy, i.e. HHF, is greater than the work function, W, the leftover energy becomes the electron's kinetic energy, its speed.
So higher frequency means more leftover energy, means faster electron. Intensity just means more photons hitting per second, so more electrons come out, but none are faster.
You got it. Intensity is the quantity of photons. Frequency is the quality, the energy punch of each individual photon.
Wow, that just clicks. It completely flips the wave intuition on its head.
It absolutely does. And the amazing thing is, the guy who experimentally confirmed Einstein's idea beyond doubt was Robert Millikan.
And the sources say he spent years trying to disprove it.
10 years. He thought Einstein's photon idea was just too crazy, too radical. But his own super careful experiments ended up proving Einstein was right all along.
That's fantastic. Science working even against the scientist's own bias.
It's a beautiful example of the process. Millikan's work helped solidify the photon concept and played a role in Einstein eventually getting the Nobel Prize for it.
Okay, so where does this leave us? We've got young slits saying light is definitely a wave. We've got the photoelectric effect saying light is definitely particles, photons. What gives?
It leaves us with wave-particle duality. The unavoidable conclusion is that light is somehow both. It behaves like a wave under some circumstances, like when it passes through slits.
Charging interference.
And it behaves like a particle in others, like when it knocks electrons out of metal. It's not either. It's both hand, depending on how you poke it, how you measure it.
Mind-bending. And this isn't just for light.
Nope. That's the next leap. Louis Broglie had this brilliant idea. If waves, light, can act like particles, photons, maybe particles like electrons, protons, matter can act like waves.
Matter waves. So an electron can have a wavelength.
Yes. He proposed that everything has a wavelength related to its momentum. It's just that for big, heavy things like us, or a baseball,
The wavelength is ridiculously tiny, Too small to ever notice or measure.
Exactly. But for something really small and light, like an electron, the wavelength is significant enough to be detected. And it is. Electron diffraction is a real thing, used in electron microscopes.
So this duality is universal. Waves act like particles, particles act like waves. Wild.
It is the fundamental nature of reality at the quantum scale, which leads us directly to the big philosophical implication.
Heisenberg, the uncertainty principle.
That's the one. Werner Heisenberg figured out that if things have this dual wave-particle nature, there are fundamental limits to what we can know about them simultaneously.
And crucially, this isn't about having bad measuring tools, right? It's built into the fabric of reality.
Correct. It's an intrinsic property, not a technological limitation. There are pairs of properties, like position and momentum, that are linked in this uncertain way.
Okay, explain that link. Position and momentum, delta and delta P?
The more precisely you measure the position of a quantum particle, say an electron, the less precisely you can possibly know its momentum, basically, where it's going and how fast.
And vice versa. Know the momentum really well.
And you lose information about its exact location. There's a trade-off, defined by Planck's constant again. You can't have perfect knowledge of both at the same time.
Oh, no, what stops us?
The very act of measurement. To see an electron's position, you have to interact with it, maybe bounce a photon off it.
Okay.
But that photon carries energy and momentum. When it hits the electron, it tells you where the electron was, but it also kicks the electron, changing its momentum in an unpredictable way.
Ah, so looking at it changes it. You can't measure without disturbing the system.
At the quantum level, yes. Measurement isn't passive observation, it's an active interaction. And there's another key pair the sources mentioned too.
Which is?
Energy and time. Similar relationship. The uncertainty in a system's energy, delta HACI, is linked to the uncertainty in the time interval over which you measure it.
So a very precise energy measurement takes a longer, less defined time.
Or if something happens very quickly, its energy is inherently a bit fuzzy. It's this fundamental fuzziness that replaces the old clockwork certainty of Newton's physics.
We've gone from a predictable universe to a probabilistic one, where we can only talk about the chances of finding a particle here or there, or having this energy or that.
That's the heart of the quantum revolution. Determinism breaks down at the fundamental level. It's inherently uncertain, unpredictable in a way classical physics never imagined. It links, interestingly, to ideas in chaos theory, too, like the butterfly effect, where tiny uncertainties blow up.
Okay, let's try to wrap this up. We went from Newton versus Huygens, wave versus particle,
to waves seemingly winning with Young and Maxwell.
then Planck hitting the wall with black bodies, inventing quanta almost by accident.
Einstein running with quanta, explaining the photoelectric effect with photons, bringing particles back.
Leading to de Broglie extending duality to matter.
And finally, Heisenberg showing us that this duality means there's a fundamental limit to what we can even know. That's quite a journey.
It really is. And the amazing thing is, this isn't just abstract theory. You mentioned solar cells earlier.
Absolutely.
Yeah.
Solar panels work precisely because of the photoelectric effect. Photons hitting silicon, knocking electrons loose, creating current. It's quantum mechanics powering our homes.
So this deep dive shows how that century-long puzzle about light unlocked a completely new understanding of reality, one we use every day.
It truly did. And it leaves us with some pretty deep questions, doesn't it?
Like what? Give us a final thought to chew on.
Well, building on that uncertainty principle, the idea that observing changes the system. If a photon only acts like a particle when we measure its path, or an electron's position is indefinite until we measure it, it makes you wonder, doesn't it? Does a definite objective reality exist before we observe it? Or does the act of observation itself somehow bring reality into focus?
Whoa. Does the universe need an observer to be definite? That's yeah, that's something profound to think about.
A good place to leave it, perhaps, until the next deep dive.
Definitely. Thanks for guiding us through that, and thank you for joining us on the deep dive.